This is Mark with your Advanced Assembly Technology Minute.
Hi, I'm Mark. I'm an engineer just like you. Well, not exactly like you. You see, lately you've been making some bad choices and some of the other engineers have begun to talk. I kind of want to put an end to it, so I hope you don't mind pulling you aside like this and having a one-on-one and maybe talking about some better way to do things. You know, I'd hate for your reputation to end in tatters. You've done so much good work so far. So, to make this feel a little less like an attack though, let's back up 30 years. So 30 years ago, I was, probably just right before a preteen age, probably about 12 years old, and I'd go down to Radio Shack. I'd make my parents take me, and I'd have them buy me these little electronic kits that I'd solder together, and a lot of those kits had parts that looked just like this. Here I'm holding 3 different value ceramic capacitors. And back then, if you wanted a different value capacitor, they would come in a different package size. Small capacitance, small package. Big capacitance, big package. Makes sense, easy enough. I mean, that's not the case today. I mean, today you can go out and get all sorts of capacitances in particular part sizes. Anything from an 010-005 to 0402, 0603, 0805, 1210s, it just keeps on going. But it's completely possible to go out right now and buy a 0.01, 0.1, and 1 microfarad capacitor that are all the exact same package size, say 0402. Didn't used to be that way, but it's certainly that way today. Well, that's kind of what we're getting to, or at least building up to. So, integrated circuits have a silicone die that takes all of the different transistors and resistors and other parts, and it shrinks them all into this one little tiny piece of silicone. And then that silicone is connected to a lead frame. Those are the pins and things that you see coming out of your thing with these little bond wires. So it'll go from silicone die through a bond wire to lead frame, from a lead frame through a trace to your part. You know, your decoupling capacitor maybe. Back through the capacitor, through another trace, into another pin on the lead frame, and then back into your IC. And that large area, that creates a very large loop inductance, or at least large enough to matter. Now, when something in your integrated circuit switches, maybe a digital logic pin goes from high to low, or low to high, that creates a large change in current, DI. And modern electronics do it very quickly, so that DI happens in a very low DT. So even though you've got, a relatively small inductance, L, if you've got a small enough DT and a decent DI, that can create a huge change in potential. And when I say huge, of course that's relative. We're talking maybe 1 or 2 volts. But that can be enough to disrupt your circuit. See, the issue happens because of that loop. That loop, that inductor, allows the reference 0 volt on this IC die to be different from the reference 0 volt in your circuit. Did you catch that? The voltages can actually be different during that switching time. So 0 volt on the board is not 0 volt on the IC die anymore. On the IC die, it's higher. Well, what does that mean? Well, that means that all of the digital logic that is measured against that 0 volt now has a new reference 0. So if you've got logic coming into your IC, right? Pins that must be defined within particular voltage ranges. They're ill-defined in the middle. Well, you've now shifted where 0 is. It's possible that the digital logic coming in is no longer defined, and your IC is no longer a digital part. In fact, we don't even know what it is anymore. It's not analog either. It's just something. It could be doing whatever it wants. We don't know. All right, so let's take a second and put it all together. Back in the day, engineers would minimize that loop inductance by using the smallest physical capacitor that they could find. That would give them the lowest inductance possible. Okay, well nowadays we don't have that problem. Now we can get whatever capacitor we want in, well, within reason, in whatever package size we want. So it's completely possible then to have a 10 microfarad capacitor and a 0.01 microfarad capacitor in the same package. If you're trying to minimize ground bounds, guess which one you should choose? It's no longer the 0.01 microfarad capacitor because that's no longer a concern. The package size is uniform nowadays. It didn't used to be. But engineers keep using this antiquated rule. They'll go out on their boards and they'll put in a 0.01, a 0.1, and maybe a 1 microfarad capacitor, trying to, kind of hedge their bets a little bit. And there's some physical basis behind it that used to make that a decent enough idea. But now that we've got these small packages, it's just not the case anymore. Go ahead and grab that 1 microfarad or 10 microfarad capacitor if you're using it as a decoupling capacitor. It most likely will have the same equivalent series inductance as, any other one. Anyways, if you want to learn more, don't want to make mistakes like this in the future and be the butt of everyone's jokes, come hang out with me over at aapcb.com.
If you liked this video, let us know by clicking the like button at the bottom of the screen. But don't stop watching now. We have other educational and informative videos on this channel. To learn more about what Advanced Assembly offers and how we can help you, please visit aapcb.com.